So welcome to the first day of data mining. Hopefully you're all in the right room. This is CS 5140, 6140. So the plan today is I'm just going to go over an overview of what the class is about, kind of an introduction to what we'll be talking about in the class and kind of the themes we'll be seeing throughout the semester. So I'll be doing that through these slides, and then I'll talk a bit about after that I'll talk a bit about how the class will be run, kind of go through how to use the web page and how various things are going to work. So if you haven't noticed, there's a camera up front here. So we are videotaping the lecture. After this lecture, we're probably going to transition to a version of the screen capture instead. But if any of you have any issues with it being videotaped, please talk to me. It is, technically allowed to videotape the classes, and so the videos will be available online afterwards, and I'll talk about that a bit when we get into the administrative part of the class. And so we'll talk about that a bit more. So for this class, I'll be talking off the slides. But in the future, instead of talking on slides, I'm going to try and work with a tablet. So I'll be writing up here. I think it's a little bit better to see things develop instead. So don't get the impression I'll be off slides. I hope the lectures, I feel, can be a bit more dynamic if you're developing them as you go. So let's see. So what is data mining? So I first started teaching this class a few years ago. There was no data mining class here, and so a lot of people were asking me, what is data mining? So how is this different from machine learning? Is it just machine learning on large data? Is it finding some structure in data? What does that mean? Is it just is this just unsupervised learning to then make it a subset of machine learning? So is this kind of just doing statistics but doing this on large scale data? So it's kind of all these things. Though the way I view this class is that it's this class about how to think about doing data analytics. Okay, so there's lots that goes into doing analysis of data. There are lots of different techniques, and we can't cover all of the techniques in this class. This requires like a whole degree to understand all of the techniques you need, but I'm going to try and talk about a lot of the core techniques in various areas, and I'll kind of outline what those are. But more generally, I want to kind of try and give some impression of how to approach these problems in general. So how to think of getting some raw data and transforming it into something that you can analyze, and then how to formally analyze that, and how to do that. This is a computer science class, so how to do this at scale with lots of data, how to automate this analysis. Okay, and so one way of thinking about this is what can you recover from data and what can't you recover, right? If you just have a few observations of some very large data set, you shouldn't expect to recover kind of every detail of the individual data points that aren't viewed from your data. So there are certain things you can't reliably recover, and part of this because there's noise in data, part of this because often it used to be the old view was that we've collected some subset of data we have, I asked every person in the class what is their birthday, and then I have all of the data that was necessary for me to understand something, right? But it's more and more that people are realizing they're collecting data, say the birthdays of your class, and that's not interesting for understanding the birthdays of the entire population, right? Say I wanted to say whether there were more birthdays in September than there were in December. So it turns out there's slightly more people are born per day on average, more people are born in September than in December. But if I just ask this class, it's possible it's not going to back that up. So there's some larger data set that you want to understand, and often you don't have all the observations. And so also, as we're in this age where we're able to collect larger and larger amounts of data, there are these kind of older statistical techniques of analyzing these data sets, but they don't always scale. So you need to think of the algorithms that can allow you to take this analysis and scale it up to the size of the data that you have. And so sometimes you can't apply like the full analysis you'd want to. You have to kind of take the data and convert it into some other format or kind of some representation where you know of an algorithm that can scale. And there are trade-offs. Okay? And so one of the key themes is going to be kind of finding some way of analyzing your data that fits on this continuum between the most precise modeling you can do and the efficiency of the algorithms that you're running. Okay, and so there's data mining, there's machine learning, and these are both classes being offered here this semester, and they both fit probably somewhere on this continuum. At least the way that we teach it here, probably machine learning is a little bit closer to the statistics, and this data mining class is a little bit closer to the efficiency side. We're going to focus more in this class on scaling to very large data sets. We're going to be talking about some of these paradigms which are going to be fairly loose in the analysis. They're going to be fairly crude, but they'll allow you to scale to very, very enormous settings. So in a lot of the cases that you'll deal with data, you're really trying to pull at these two ends. You have something you want to analyze, and you have to make some choice of, are you going to run kind of some very detailed kind of analysis where you have to kind of clean and try and understand every data point at a certain amount? Or are you going to say, I want to keep this analysis updated as more data points are coming through, so I have to do it extremely efficiently? So you're going to make some trade-offs between these two things. And so this class will be about understanding these trade-offs. So if you are interested in machine learning, again, there is this other class that's going on. It's from 3 to 4:20 on the same days, also on Mondays and Wednesdays, and kind of again a very crude way of understanding the difference between machine learning and what's happening in data mining is that the core of machine learning is understanding how to build a classifier on data. So you're given some data points, and they're labeled something like true or false, or maybe there are multiple classes. These are corresponding. Maybe if you're a company, these are people who are making you money. These are customers who are losing you money because they're taking more effort to deal with them than they actually generate profit. And you're given some new customer, and you want to understand whether they're going to make you money or not. And so this gives you some sort of label. You want to try and predict something about some customer without seeing this label. Okay, so this is classification, the core, and that's kind of the central kind of goal of a machine learning class. And because there's another class covering this, we're not going to talk much at all about classification in this class, although it comes up in certain tasks in data mining as well. Another kind of way that we have chosen to kind of differentiate these classes is that the machine learning class will be more about some continuous optimization. So it'll be more about, there's some sort of mathematical formulation that you say, this is what I describe as a classifier, and then we're going to kind of iterate in some way to try and solve for that. Whereas this data mining class will be more discrete. We'll be more saying, okay, there's a space of possible solutions, and we're going to search kind of this discrete space of possible solutions, or use these techniques where we're going to kind of look at a finite number of possible ways something could be, and optimize over those in a discrete way. And maybe this will become more clear over the semester, especially for those of you who are taking both of the classes. But so this divide is fairly arbitrary, and we've chosen to do this just because there's so much material here that we want to teach 2 classes, and we didn't want them to be the same class, right? So we've kind of arbitrarily split them. There'll be some overlap between the classes, but not too much overlap. Okay, so also this area of data mining has been changing fairly rapidly. So when I was in graduate school, I took a data mining class that I was taught in the math department, and there was a certain view that they had on what was going on what they had was going on in data mining. There are others that have been taught in computer science departments, and these have been taught for more than a decade. And so there are some fairly old and standard textbooks on these. And we aren't going to follow most of either of these 2 views, maybe somewhere partially in the middle. But this class will focus especially on the large-scale aspects of the way we understand data. I'm going to try and give a fairly broad coverage of a very different topics that I think are making up what people are most excited about in the area right now. And I'll try and throw in in each general area, I'll try and throw in some recent developments. So probably kind of a quarter to a third of the lectures are things that were really not even thought about as few as 10 years ago. So sometimes only 5. Right, so every semester I've taught this, I've updated a few of the lectures with some recent developments that have been happening. And so these are not available in a lot of these older textbooks about that were about data mining because they hadn't been developed yet. So we'll try and the course which is probably closest to this, and I'll mention this when we talk about that administrative stuff, is there's a Coursera class at Stanford, and so they have a book, and I'll link to some aspects of that book. So that class is probably less formal than this class. This class is split about 1/3 undergraduates and about 2/3 graduate students. And so that class is designed to be mainly undergraduate students. So this class will be a little bit more mathematically rigorous. We're not always going to go through proofs of everything that's going on, but we'll at least try and sketch the proofs, and I'll talk about some ways you can formalize a lot of these concepts. That'll be the way it is. So it's most different from that class. Since I started teaching this 4 years ago, there have been a few other classes around the country and the world that have taken a fairly similar flavor to this class as well. So I think part of the reason of that is that the topics we cover here are topics that a lot of the companies that are processing a lot of the data on the internet have been kind of making up the core of what these companies do. These are kind of the core tools in understanding the large data that they've been processing. And so it's not necessarily always the fine-grained details of how they apply it on certain things. I'll try and make these connections, but I'll talk about the general tools that hopefully will survive, beyond just what's going on in these internet companies now, but it's going to be persistent as more and more of these, more and more companies are trying to process and understand their data and drive value from this, and also in science and engineering as people are also driving kind of value in terms of moving research forward based on all the data they're gathering. So I've, in the past, students who've taken this class have gone off and done these job interviews with a lot of these Bay Area companies, and a lot of the topics that we've we have covered in this class have come up in discussions of what they'd be doing and have helped them on the job interview. So, you know, I've been pleased with how the coverage has lined up with that, and I hope, you know, I'll hope to continue kind of keeping the course modern to keep it up to date with all these recent developments. So the other thing that maybe differentiates this from more classic classes in data mining is that this is really kind of it really looks to be kind of a midway between these computer science algorithms and statistics. So we're doing a lot of probabilistic algorithms, these randomized algorithms, where either we're taking some fixed data set and we're running some randomized algorithm where we use randomness to kind of process it very efficiently, or where we assume that the data is coming from some underlying random process, and then we need to kind of use this understanding of how this randomness works in order to derive proper value from the actual data. So that's kind of, you know, one of the themes. So a lot of people have asked me, are there any specific software tools or any programming language that we're going to have to be using in this class? This is not going to be based on a particular type of software. We're not going to just be using like Tableau or something, or just just doing everything in R. We're going to kind of be working on the principles, and the assignments are going to be fairly flexible in how you do them. People have done the assignments in this class and just about they've done them in just about every language you can think about, right? I've had people who are more senior who only knew how to program in Fortran, and they managed to get through the class mainly in Fortran. Some people have done it, just Camel or whatever. There are going to be some parts where it's going to be much easier to do them in MATLAB. You can do them in R pretty easily as well. These will be things dealing with linear algebra, and having a language that can deal explicitly with matrices will make life a lot simpler. And you don't need MATLAB license if there's a free open a free version called Octave, which will be just fine for the class. So don't worry about buying MATLAB. It is installed on the CADE machines. So the main math tools that will be useful for this class are going to be linear algebra, probability, and high-dimensional geometry. Okay, so I kind of expect you to have some knowledge of linear algebra. Okay, linear algebra is how you deal with data in the form of a matrix and doing matrix operations. We'll kind of review some of the core things, but we'll do it very quickly. So if you haven't ever seen any of these things before, it'll go very quickly for you, and you would have to do a lot of work to catch up if you haven't seen it before. And I also expect some knowledge of probability. You should understand what the expected value of a random variable is, how to understand conceptually what the distribution of a random variable is, and so we'll talk about this, including the lecture on Wednesday. We'll kind of very quickly go over some very powerful, but kind of somewhat advanced for people on CS at least. Some things about probability. And we may not need to use these tools very explicitly in the rest of the class, but you'll need to understand them conceptually for a lot of things to make sense. So they'll be kind of a simplified version of what's going on. And so then the third one is high-dimensional geometry. And this, I don't expect you to have as much background in. It's a really cool area, and I plan to kind of teach you a lot of cool stuff about high-dimensional geometry. And this is really an important kind of math area that's related to the analysis of data. Very often you kind of take various sorts of data and you translate it into a problem that deals with some high-dimensional setting, And then you can use the underlying math to understand what you can and cannot analyze about the data. So we'll see some of that in class. Okay, so it's going to be in between understanding this mathematical formulations of the data and then the algorithms and the programming needed to extract that information. So we're going to kind of be between these two areas. Okay, so what is the kind of the outline of what's going on in the class? So we'll kind of start by understanding these kind of, we'll talk just a lecture or two about understanding like some basic properties of random effects. And then we'll see these as a theme that's going to happen throughout the class. The basic, and so then we'll talk about what is data and what do you think of a distance between data. Okay, so there are lots of ways to view this, and there are lots of choices in how you think about this. And these choices will affect how you model it. And this will allow you to understand certain types of structure in the data. So the structure is presumably what you're mining for in the term, data mining. And they're really kind of, there have been a lot of thoughts about what can you find, what kind of structure can you find in the data, and there have been a lot of various research directions and companies formed around different aspects, but they really can usually be traced back to one of a few things. Either you're clustering the data in some way, or you're finding some sort of linear representation of the data. And so we'll talk about these. Or maybe there's some sort of noise in the data, and you're trying to kind of work through how to understand and deal with this noise in the data. So these will kind of be the core types of structure that we'll try and look at. And so then you'll need to deal with this noise and the uncertainty in there. And one of the other things we'll do within this is we'll look at these large graphs. This has become very interesting because of people who've been studying these social networks. And so in understanding these social networks, you really model them as graphs. Now, that's not the only place the graphs come up. The whole internet you can model as a graph, and this becomes very, very important modeling as well. So we'll talk about these areas. So let's kind of break these down in each point in a little bit more detail. So the kind of statistical principles that will kind of be interesting is what happens when you see data that's kind of coming from some underlying distribution. Kind of what can you say about data that's coming from some distribution? And we'll kind of overview this by talking about one of the simplest distributions where it can be each data point you see is basically going to some element in some array. And each one is independent of every other one. Okay, and so then this can represent, each element of the array could represent something like an IP address, or a word, one of the words in the English language, or an edge in a graph, or just a hash table data structure. And then what there are certain, there are these certain phenomena that happen. One is you keep generating data points until you have a collision where you have two land in the same spot. Right? And this ends up being important, and you should understand that this can happen regularly, and this is not some big kind of insight that you've derived from the data. This is part of a normal random process. And then the next step is when you do this until you have a data element in each of the buckets. Right? It's not going to be just the same number of points as there are buckets. You're going to have an overfill in a lot of the buckets before you see all of them. You should understand that this doesn't happen right away. This happens once you've kind of overseen all the data before you fill in all the buckets. And then the third one is when all the buckets are about the same height. And this is a little trickier to define. But you want to say, you keep doing these random trials, how representative is any one of these elements of the whole underlying distribution? They're never going to be exactly the same. If this is the average at this line, they're never going to all be exactly that line. There are going to be some less and some more, but when do they all about the same so that you can trust it? And how do you quantify this? Okay. So, and one of the key kind of themes here is that we're going to be mapping from some sort of raw data that represents various phenomena to some abstract setting. And this was one of the simplest versions of it. You took this data, which are maybe IP addresses, and you mapped them just into this array. It's a simple idea. We can study the data that falls in this array, and we want to have the same phenomena to be able to study for many different settings. So we map it to this abstract representation. And maybe, for IP addresses, this is not the normal kind of way of doing this. It would be a uniform distribution, but that's just an illustration. There are many other ways that you're going to kind of get these abstract representations of data. The first thing we'll be talking about is taking text and transforming this in some way so it represents, so you can represent text as either points in a high-dimensional space or as these elements in these sets. And so so if you're points in a high-dimensional space, then there are a bunch of algorithms you can apply on those. If there are sets, there are algorithms you can apply on sets, right? So we're going to map text into sets because text itself is really hard to analyze. So we have a class that's offered on natural language processing where you talk about uncovering all the elements that make up a sentence and breaking this down. And this is a very time-consuming process that people spend years doing. And it's hard to do at very large scale. So if at very large scales, you want to have a more kind of a more abstract representation where you can run faster algorithms on it. Other things are graphs. So if we talk about we'll model something like a social network as a graph, and then we'll convert this graph into a matrix, and then this matrix you can convert into high-dimensional points. And depend on how much modeling you want to do and how fast you need the algorithms to be, you're going to want to go from one of these settings, whether it's graph, matrix, or high-dimensional points. And so and we'll look at different trade-offs of these. We'll also look at just these tables of values. This would be like a typical table in a database. And again, you can think of this as high-dimensional points. But there are some pitfalls if you don't do this correctly. So we need to kind of be very careful when you do this. You kind of lose some information about the data if you go to some of these abstract representations. And so we'll talk through these for a lot of these different settings. Okay, so then the next theme was the one on the distances, and we'll often talk about this through the idea of similarity instead of distance. And these kind of points are, if they're close, they have a high similarity but a small distance. They're kind of duals to each other. So the sort of questions you'll want to deal with is you have a large data set P, and given a new point Q, is Q in the data set? Okay? And maybe you have some noise on Q, so it may not be in there exactly, something very similar to it, which you think is probably the same thing. Is that in the data set? You want to do this without checking every single data point, because that's going to be too expensive. So how can you do this more efficiently? And or another question, which is very related, but not exactly the same. If you have this large data set and you have this query point Q, what is the closest point in the data set to Q? And so I'm saying data point now as this abstract representation. This will be easier to think about. But this doesn't need to be a data point. It could be a row in a database. It could be a node in some graph or a person in a social network. Right? So it can mean lots of different things when I talk about this. But we'll translate this into some setting where we can define some similarity or distance and then look at some of these algorithms that we can apply. Once you have these notions of distances between points, this is often all you need to start talking about clustering of this data. And this is taking this large data set and breaking it into these subgroups, which are every element in the subgroup is similar to every other element, but maybe different from the other elements that are in the different subgroups. So this is a very vague definition, and that's because there are lots of ways to define clustering. And so in this class, we'll talk about kind of three core ways of defining ways of doing clustering, and we'll pinpoint some of the kind of classic and some of the very recent algorithms for doing these at scale. So there are various questions of, do you need a representative from every cluster? You know, if you have a cluster of data, do you want some representative point to do that? Some clustering algorithms which work very well don't give you representative, where other ones do. Can the clusters overlap with each other? And what are the effects of changing the distance used, or the type of data you're using? These are kind of questions we'll try and tackle in the class. And we'll go through kind of these three kind of core ways of doing this. One is this hierarchical clustering, where you're kind of building a lot of structure, but it's a bit slower to do this. One is this k-means type clustering, or other kind of things like k-means clustering, where you're assigning these representatives and mapping everything in the cluster to a representative. And this allows you to actually compute the clusters more efficient and have a lot of nice properties about them. And we'll also talk about clustering in graphs. So if your data is not just elements with the distance, but is actually defined by this network, how do you kind of build clusters within the graph? And these are kind of, so it'll be three different themes. But you know, these are just going to be three topics within a very large space of material. And in fact, there's another class being offered that some of you know about that's just on clustering. So it'll be a full semester just on this topic. We have 3 lectures on this. There'll be a full semester. And so this is a large class. The clustering class will be much smaller. So you'll get a bit more kind of deeper into this area. Okay, so the next kind of structural thing we'll look at is going to be regression. And so this is a fairly kind of broad, this is a fairly broad topic as well. And again, we'll be kind of hitting on some main points. Again, my attempt to define the whole area is you're given some data points, often in some high-dimensional space, although this isn't necessarily the case. And often for these modern applications where there's been a lot of development, this is where the dimension of the space is very large. We'll talk about what that means. You want to find a lower dimensional subspace represented. So this is, if you've heard this term, dimensionality reduction. That's what we're talking about here. So this can mean different things. Either you want to find the subspace so the distance to that subspace is always as small as possible on average, or in the worst case, or you want to find so that the distance in the full space between, say, this pi and pj is going to be similar to the distance in the projected space, the qi, qj. So you want that to be true for all the data points. You know, and there's various ways of defining this, and we'll talk about. We'll try and talk about a few of these in the class. This corresponds to lots of terms you may have heard, so either like things like least squared regression, or PCA, or multidimensional scaling, or these ways of doing these random projections to do dimensionality reduction. And then there are these other kind of newer developments. There's, instead of doing the standard least squares regression, there are these L1 variants of this that are that end up being more robust to noise. And these have to do with like these ideas like compressed sensing, which is like a whole new field which is not around 10 years ago. It's a way of when your data has some amount of noise, but it's a limited amount of noise and certain specific types, you can recover the true underlying structure, in spite of the noise, exactly, in certain ways. And so this is based on these more robust ways of doing regression. Okay, so this whole notion of compressed sensing is something which probably deserves its own class, and it would be probably an advanced graduate class. But we'll try and cover this. We'll get to the point where you understand what it is and some very basic algorithm for how to do it. Okay, and we'll give you pointers towards a lot of other things. But we'll cover in more depth how to do these things like just regular least squares regression and PCA and multidimensional scaling and stuff like that. Okay, and so these basic techniques for dimensionality reduction. Okay, and so like essentially one of these lectures we'll spend in the class. There's also another full class on this topic. This is a 1-credit seminar that is held on Fridays. This is something else I'm teaching. Again, this will be a much smaller class, more focused and more in depth. If you're interested, you can take that as well, or you can also just show up, and that would be fine. Okay, so then one of the other topics we'll talk about is how to think about and deal with noise in data. And this is a very kind of, even more so than these other things which I had trouble defining. This is even more of a vague topic. This is something very common to data mining in that you aren't necessarily given a, like if you take a class in algorithms, basically you're often given a specific task that you want to solve. You have this input data and you want to get specific output of the data. In data mining, you often struggle to define what it is that you want to solve. And then once you know what you want to solve, you apply some standard algorithm that we'll talk about. And with understanding noise, you have to think about what kind of noise you get in data and what does it mean to try and deal with it. And there'll be, so like one of the tasks is to try and identify outliers and then say let's try and remove all the outliers so that when we run a task on the rest of the data, it's more accurate, right? Or try and model it. Maybe the outliers are the specific elements that you want to identify because those are the most interesting part of the data. There are also these ways of trying to exploit the noise in data, and this is kind of a different way of thinking about it. But if you add a small amount of noise in the data, you can often still recover similar of the core structure. These clusters or this regression we're doing, but obscure any individual one of the data points. So that if that data point represents you, that someone can't know your personal information even though they can mine something in the aggregate. So a company may want to promise their customers they're going to not reveal too much about each one of them, but still do some mining so they can understand how to generate profit from the data. Okay, and so there's this idea of differential privacy, which we'll touch on about doing this. We'll also talk about kind of the ethics of doing some of these things. This is kind of an important topic with all that's going on with the big data center from the NSA. That's opening close by, and also all these other things with these internet companies generating value from the data. What should you and shouldn't do with the data, and what are some consequences of not thinking carefully about what this data represents? Okay, so then the kind of the last major area we'll talk about is going to be this link analysis. And more generally, this is basically talking about modeling data as graphs. But this is really, one of the most interesting applications of this, one that kind of really woke up this whole one of these whole movements, was when Google started. The way the company was brought off the ground was they modeled the entire internet, the entire web, as this large graph. And that's what differentiated them from all these other search companies at the time. And so they model as a graph and were able to drive value from this graph in order to improve the search results. And so we'll talk about how they did this with this PageRank algorithm, how they're able to model as a graph, and how they're able to kind of exploit this. But then there's this interesting trade-off between these people trying to spam these search engines and the modeling using as a graph. And the graph was, because of the structure, they're able to get all this, the structure is more resilient to these individuals who are trying to spam the search engines. And so there's kind of a really interesting story there. To understand this really deeply and to the full extent, you need to start with this mathematical concept called Markov chains, which actually has uses in many other areas as well. But it's kind of the core way of thinking about these graphs and how data moves around these graphs. So if you heard of this term like a random walk, a Markov chain is a way of modeling this random walk. Okay, and so then we'll also talk about how this platform of MapReduce grew out of modeling this data as a graph. This is a very scalable system. Hopefully many of you have heard of MapReduce or Hadoop by now. It grew out of running this PageRank algorithm at very large scale, as long as, in addition to, at the time, Google's other core computational task, which was building the search engine on top of them. Those two core tasks, they needed to run extremely in parallel, and MapReduce was a way that allowed them to do both of those. And then they found uses in many, many other ways. And with graphs, we'll also talk more about finding these communities. And this is related, again, to the clustering problem. But again, clustering is such a big topic that when we talk about clustering, we won't talk about the communities part. There are whole different notions of how to find these subgroups within the graph that kind of are very strongly connected and the sort of value you can get out of that. Okay. One other theme which won't have an explicit section within the class but will kind of be sprinkled throughout is the idea of taking a really large data set and creating a small summary of it. And this will allow you to kind of do the analytics then on the summary very quickly. You can then revert to some more classical statistical techniques, which may be much slower, but because you preserved a very large data set into something much smaller. And we'll see this in various settings, in graphs and in one of these large data settings called streaming, where your data is coming in one element at a time and your memory is limited. So like you're sitting on a router and you want to maintain some statistics on there. So you can do some fairly crude statistics at very high efficiency and with very small space. And so this is kind of, there are these, again, trade-offs between this is very far on the efficiency side and not quite as far on the side of statistics. But this is one of the things we'll talk about in the trade-off. Okay, so again, the main themes for the class, we're going to, we can't cover every single topic that, is relevant to data mining. There's big conferences that have, there are hundreds of relevant new papers every year in data mining on certain special topics. But if you're, so we'll try and talk about the kind of the really main things which are touch on many of these special topics and are very prevalent throughout. And so with that, I want you to really build an intuition for how to think about this data. So when some new topic pops up, you can relate it to one of the things we talk about and how to get from some core or some raw, messy data into some format you can understand and process. Okay, and so this has to do with how do you model the data? How do you take something where you've collected these logs on some server and you convert it into something that you can run some algorithm and analysis on? And then how to do this efficiently. Okay, so we're not just going to talk about what is the representation of this or the mathematical concepts, but how to make sure that these are the concepts which align with ways that can be done efficiently. And we'll see this trade-off in many different aspects. So I want you to come away from the class thinking about what is the right way to model the data in some way I can represent, and how to do the analysis on it efficiently once I have it in that representation. So the kind of general plan will be each of these topics we talked about. We'll spend 2 to 3 weeks on each of them. We'll overview kind of the very classic techniques that you should really know coming out of any data mining class, I feel. And we'll focus on the model efficiency trade-off. And so we'll try and, so this class is a fairly broad spectrum. There are maybe a quarter to a third of you are not in computer science. A third are undergrads. 2/3 are graduate students, and some of those are PhDs, some of those are masters. So I'm going to try and, there'll be some special topics which I'm going to go through fairly quickly to try and kind of give you a dive deep into sort of these kind of cool areas. And so for some people, these may go pretty quickly, but I hope they keep it relevant for everyone in the class as well. For each of the kind of topics, there'll usually be one homework assignment. So I think there are 6 homework assignments, and these will make up 45% of the grade. They'll have some analysis where you need to kind of understand the underlying math and some processing with the data. And they're trying to set up so that you have to do, if you just look at one or the other, because there's so many new concepts, it's going to be easy to make a mistake. Right? But if you do both correctly, you can use the data to check your analysis. You can use the analysis to check what you did with the data. Okay, so I want you to be looking at both. And these homeworks will be, I'll try and make them fairly clean, so you don't have to deal a lot of munging around in the data. If you become a data scientist, probably, unfortunately, a large amount of your job will be kind of changing the format of your data from one way to another and looking it up in these databases and so forth. And that's not always a pretty aspect. And the homeworks will try and focus on the core techniques, and I'll try and make the data fairly clean. To complement this, there's also a project, which will be another 45% of the grade, where I want you to go and find some perhaps fairly messy data set. And then you're going to go through the whole process of taking this raw data set and converting it into some abstract type and doing some analysis on it, and kind of see a more extent of the whole pipeline, and get your hands dirty a little bit and get deeper into some area that more interests you. There's so much being covered in this class that I want you to kind of find some aspect which really interests you and dive deep into that. You'll learn a lot more that way, where the homeworks will try and survey everything. There are also going to be 2 quizzes which will make up 10% of the grade. These are around halfway through the class, and at the end, I don't want them to be kind of a major concern for you. I don't want to call them a midterm and a final. They'll try and be more loose than that, but I want to kind of help you make sure you reinforce all these ideas and you study for some quiz for them. Okay, so all the homeworks will be managed through Canvas. Did everyone get an email from Canvas? Did anyone not get an email from Canvas? Okay. Okay, so if you're signed up for the class, I made an announcement. Maybe if you didn't officially sign up until recently for some reason, you may not have gotten it yet, but there's this Canvas system. I made one announcement with a link to the web page on it, so forth. So all the homeworks will be turned in through Canvas, as well as many of the project aspects as we can. And we'll use that as a discussion forum, and all class announcements I'll make will be coming through there. Okay, but the class will otherwise be managed through a web page. Right, so again, the programming there'll be some programming in the class for you who are not CS students. It's not meant for people with the programming background and CS background. It should not be too hard to do the programming. It's meant to kind of just get you used to doing it. For people without CS background, you may need to do more work to get the program to run, efficiently enough to work on it. But it should not be too hard, and we're generally fairly flexible on this. And the homeworks will try and have some bonus questions, again, to keep it interesting for some of the more advanced students in here. They'll allow you to get the kind of extra credit. So if you're asking me at the end of the semester, will there be any more extra credit? The answer will be there was some of these bonus questions, and these maybe can help you move between like a B to B plus type difference in the grade. Okay, so a couple other notes before I go to the web page. The other thing you're welcome to participate in is that a bunch of the faculty who work in these data analysis have a group meeting that meets once a week. You can take it as a 1-credit seminar if you want. But this is on various topics in the field. We'll invite speakers in to talk about in other areas what they're working on. There'll be some visitors from other universities. This Thursday, there's a researcher from Yahoo Research who will be coming and talking about some of his recent work on large-scale parallel algorithms. And so you're welcome to kind of go to this and find out more. It's open to everyone. Okay, One thing I'd like to mention, there's this cool event that's taking shape that I've been recently found out about. It's this Utah Data Analytics Summit. It's January 22nd. It's at the eBay headquarters, so it's right on tracks. It sounds like it should be pretty interesting. It's a bunch of the analytics companies in Utah, some talks by people in analytics and some CTOs and CEOs and also some venture capitalists. And a lot of companies will be there actually recruiting people who are knowledge, like apparently what I've been told what's taught in this class. So if you're looking for interesting opportunities in Utah, this might be an interesting place to go. If you're interested, come talk to me or go to this website. You can find out more. Okay. So the next thing is the course webpage, and hopefully all of you got that email with the link to it. So it's everything that you need to know about the course except for the stuff on Canvas will be on the webpage. So the main thing here is going to be the schedule, and when you see this, every day has a row and all that stuff. So what will be useful is this topic column is going to be a link to some notes that I produced. And the lectures will follow these notes, we'll try and follow these notes fairly closely. There's more kind of interesting information that'll happen in the lectures. I'll develop it, I'll explain it a bit more. But I'll try and, I try and be fairly thorough in these notes, and I think they're written up pretty well. So here's an example set of notes that we'll go through. So the other thing, so that's this column. The column, the third column is going to be it's going to be a link to the videos. So we're going to record all the videos, possibly through the camera, but I think starting Wednesday I'm going to try a different screen capture approach. We'll be writing on a tablet and so forth. And so those will be posted on YouTube and linked off of here. We're also going to be streaming these lectures. And so this is something we piloted with one class last semester, and we're doing it again in this class this semester. If you're interested in figuring out how to get on the stream, and I haven't contacted you about already, please let me know after class so I can give you some more information. Then this links class will be links to some of the books or other resources beyond what's in the class notes. This will give kind of a different view of the subject and sometimes a deeper view into some, like maybe an interesting research paper which really lays something out in more detail. And then the assignments column, all the assignments will be posted in this column. This first one will be up sometime later this week. And they're posted in the time, on the day that they're due. So they'll be due on 5 o'clock on the day of class. So you have time to turn them in and then still get to class on time. The third and the last column is on the project. In a lot of classes you'll have a final project, and it's just due at the end of class. Okay, this project will be very different than that, in that there are going to be kind of 5 or 6 milestones throughout the class. And so this is a little trickier to do, because you'll need to start doing milestones maybe before you come to the topic that we cover in class that your project might be in. But I've tried to set them up so you can still do this. There's a document that I link off of here, which talks about the project. And there are these 5 milestones. There's a project proposal due on February 2nd. And there's this is where I want you to propose the main idea, and we'll give you feedback. If I think this is a good idea for a project, we'll say, great. Right? And 80% of people who've turned this in, I've said, this is a good idea, go for it. 20% will say, this probably isn't going to work from my experience, and I'll redirect you or say this is not really on topic. Okay. Then on February 23rd, there'll be you'll have to do a data collection report. Okay, so what people often don't realize is collecting the data to analyze is often a really painful task and takes a lot longer than you expect. So I'm putting this deadline earlier, and not everyone finishes this deadline on time. They think, oh, I'll do this right before. Data collection can take a while, and it's better you start doing that earlier. So you can start working on this before you're doing the actual analysis. So this is all building up to it. Then March 23rd, which is right after spring break, you're going to have to do an intermediate report saying, this is what I've done so far. I've started to analyze it. I've got the basic approach working, or I'm going to compare a few different approaches, and I've got the first one working, or something like that. Or I tried, I've got them set up. I don't quite have them working yet, but here's the infrastructure I built. And then the final report is due April 14th. So notice, this is not the end of the semester. This is like 2 weeks before the end of the semester. The final report will be due. Okay, and you'll have other classes where you're doing other projects typically, and you'll have so many homeworks through the end of the semester, and you'll be worried about finals and whatever. So I think it's good to have it be due a little bit before that. That way you actually have time to focus and work on this one. And then in place of the final exam in that slot, which is the April 29th, we're going to have a poster session where instead of doing presentations, you're all going to make posters, and I'm going to somehow manage to go around and see all the posters in this period. Maybe a little bit longer than 60. We'll see how it goes. But so you'll need to make a poster describing your project. And we have utilities for making posters here, so you don't have to worry about the actual printing itself if you do everything on time. But you'll need to make it, make and design the poster. And so when each of these milestones are coming up, I'll usually have a part of the actual class before that to kind of go in more detail and answer some questions about each of the pieces. But the kind of core things to start thinking about right now is how are you going to form a group. So this is a group project. I want 2 to 3 people in a group. I prefer and 3 people was in every group, but it doesn't always line up, and sometimes it makes sense to do 2, and that's okay. In rare situations, I may allow 1 person in a group. I might even allow 4 if you have a very kind of good plan of how you're going to delineate a group among 4 people. Maybe, I'm not sure. But I'd really like 2 or 3 people in a group. So this group should kind of break down some larger project. There should be kind of, if you have 3 people, there should be kind of 3 subparts to it. So I can kind of delineate that this is really a 3-person project. I don't want, there are really 2 parts to it and 3 people on the project. I should be able to say this is more, a 3-person group should be more than a 2-person group because there are 3 parts. Now when you work on it, you don't need to split it up that way, but I just kind of want you to mentally think this is a 3-person project and there are these 3 individual parts. Sometimes groups don't work out, they kind of don't work very well together, and so you need to kind of decompose the project into parts so you can come to terms without, and I can break things apart at the end. So I want to see some kind of 2 or 3 clear components of it when it happens. And kind of the main, the main scale of the project will be to, what I want you to do is to take some thing we'll cover in class and analyze this in much more depth. Right? The homework assignments will be, let's apply and see how the basic techniques work, and I'll try and design examples where the data actually bears out the structure you're trying to find, as you would expect you can find it. Okay, but with real data, it's never that clean. You want to try and do the same thing with a larger, messier data set. And some projects, and this is fine, they say, I'm going to take this large social network, and I'm going to try and cluster it. And people will come back and say, I tried all these algorithms, And I know I implemented them right, I checked all these different things, but there were no good clusters in there. And that's fine, right? I want you to try and deal with these situations and understand and make a fair assessment of whether there is something there to be found or not. Okay, and sometimes you start looking for one thing and you realize this whole other pattern. I had one group that was doing this last semester, or it was last year, and they planned to do some spatial analysis of this data. They'd gone from a company. A former student went on to be a data scientist at this company in the Bay Area. He said, I have this cool data from my company. Do any students want to work with this? And so a group worked with that data, and they were trying to analyze something, and they found the data was kind of weirdly grouped in this weird way, and they couldn't, and there's this weird structure in the data, and they found out that there was these techniques for differential privacy or data privacy had been used on the data, and they were able to realize that without being told that that was the case. So they uncovered this structure in the data when that wasn't what they were looking to find at the beginning. Right, so you'll start working on some projects and it will take you in certain areas. So it could be something where you're just taking one technique and you're really applying it on many different data sets very deeply. It could be you're taking a few of the different techniques that we talk about, maybe some other ones that are beyond what we explicitly covered in the lectures, and you're comparing these on the same data set. Say which one of these works better. And this will often be a case. For clustering, there are thousands and thousands of papers on how to do clustering, and so there you can apply many of these techniques and see how they work on the same data set. Do they really give you something different? Does one work better than the other? And so forth. And you could also kind of take some technique from class and try something new, right? So say, I think this variation of this technique we applied was going to work better. It's going to find some structure better than before. It's going to be more efficient than before. Maybe this is on a very specific data set you think this will work, or just in general, right? You could also say, here's a particular sort of data that I'm very interested in, and I want to kind of apply several different techniques to uncover various types of structure from the same data, be themed around a certain data set you're analyzing in these different ways. Okay. So it's and often, so one of the first things you'll need to do in this proposal is kind of have an idea of what you're going to do and kind of an idea of a project. And these ideas are often best when they're coming from something that you really have interest in. So whether this is, if you have an advisor you're working on in a research group, find something from that research group that interests you and turn that into a project. If you're working at a company, full-time or part-time, they may have really interesting data. You can use that data, and if there's something where we need to worry about the privacy of the data the rest of the class can't see, for whatever reason, we'll figure out how to do that work. I'd rather you find something useful that really applies to your interests, what your core, what you're doing day to day. You tend to find much more interesting projects that way. Some people have taken stuff based on hobbies, on certain hobbies they have about certain data set. People have looked at their own social networks and kind of they've said, I'm on Facebook and I have a lot of friends, and then I'm going to gather all my friends and my friends' friends and analyze, just that local data set. Okay. And if you're still struggling for ideas, there are these links to a bunch of these online data repositories with some pretty cool data sets. These cover a lot of variety of different things. And so just go in these links and just kind of browse these data sets and start looking for kind of some interesting ideas. So just kind of these are great things to browse and say, oh, that's a really cool data set. They've captured, there's these, there's like, there are these n-grams that we'll talk about in the next few lectures that Google has put online for some really large texts. So you can go through those and say, oh, I want to really analyze this particular data set, or this is really cool, this is on a topic that, yes, I have great interest in that. So go and browse these, and you'll find some cool stuff. Okay. Okay, so other things, so as far as videos go, it'll be on this link here, but there's also the CS department so it has its own YouTube channel. So if you click this link, you'll go to the YouTube channel, and this has a bunch of videos. So the advanced algorithms class was on here from last semester, and then the machine learning and data mine class will be on here. And they'll appear just in the channel, but we'll make up specific playlists for each of the classes as well, so you can keep track of them all. So I've actually videotaped my class for the last 2 years as well, and so you can find those old videotapes if you want a different perspective of something, or who knows what. If you go to my webpage, you can find the links to my old classes, and there are links to the videos. I used a different channels on YouTube before, and I switched them both years for whatever reason, so they're on different YouTube channels. But you can go and find all those old lectures if you want to, as well. Okay, so the other thing is the books for the class. So I mentioned there isn't the sort of topics we cover here. There's no great single book that covers it all. I linked to 2 books, and they're not, when I first started teaching the class, neither of these were actually books. Now, one of them is a book. This first one, this Mining Massive Data Sets, is from a Stanford class. It's now a book you can actually buy. It's also freely available online. You just follow this link. This kind of covers the general techniques and the way of thinking about this. It doesn't go always into the math as deeply as this class will. To complement that, there's these lecture notes that I thought were going to be turned into a book, but that never materialized. This is from a class at CMU, this computer science theory for the information age from maybe 4 or 5 years ago. And it covers a lot of the math that we'll talk about in this class in more depth. So it's probably not even as refined as my notes, but goes more in depth on the math that's behind this class, and much more than in this book from Stanford. And I'll try and link to the relevant sections of each of the books in each of these columns, so you can go and figure out where there's, and just give you a different view on the subject. Okay, so then other administrative things. So there's a class syllabus, just linked here. It's a PDF. You can see it. Just so officially, I show it to you. I'm supposed to show you on the first day of class. This is kind of like my contract to all of you in the class, right? So this tells you what we'll be doing, how the homeworks will be done, the grading policies, this 45% for the homeworks, 45% the project, 10% for the quizzes. The important thing is the late policy is in here. Okay, so you can turn in the homework assignments late if you want to, but there'll be a 10% penalty for every day they're late. Canvas gives me a timestamp when you turn it in. If it's if it's more than 0 and less than 24 hours late, you'll lose 10%. If it's between 24 and 40 hours late, you'll lose 20%. If it's more than 40 hours late, then it's going to be given a 0. Okay. If you believe that there's some issue with the grading on the homework, you should give me something in writing within 1 week of getting the homeworks back. And this happens, right? You know, there are 100-some people in this class. We're going to be grading all these homeworks. We'll probably make some mistakes. If you see a mistake, you know, please let us know. But please do it within a week. If these all come at the very end of the semester, it's kind of a pain to deal with. And you should look at this when you get it back. This is kind of how you get feedback and how much you understand the class, right? So you should look at it right away and ask if there are questions. It's okay to collaborate with other people on the homeworks, but you should write up everything yourself. When you write code, you should write code yourself. Okay, it's okay to talk with other people in the class. That's fine about the general approach. There's a discussion thing on Canvas. You can post a question on there. The TAs and I will try and respond quickly. Other people in the class you know, it's great if you can respond as well. I encourage a very lively discussion on it. In the past, I had like a Google group instead of Canvas. It just was a little bit hard to get everyone signed up, so Canvas does it automatically. And we had some fairly good discussions on there. The thing I don't want is you to post a possible solution. Say, I think the answer is this on homework 1A. I don't want you to, you know, is that right? That's not appropriate for the discussion group. I will try and remove those, and I'll give you a warning, and if you keep doing that, I'll come up with some sort of punishment for doing it. Usually, one warning saying, please don't do this is enough for people. Hopefully, this is good enough for that. You know, but quizzes, you know, do stuff by yourself. In the project, you'll work as a group together, but if you're worried about how that collaboration is split, I want you to kind of make a table in the appendix saying how the work was split, just so in case there's any concerns about that. So also please don't cheat. If I find cheating, you know, we'll have to go through the channels, and it's not going to make me very happy. It's not going to make you happy. If you got caught cheating twice, you're out of the whole program. So people cheat every semester. It's unfortunate. Please don't do it. It's not worth sacrificing your whole degree. Okay. If you're of any special extra things you need because of disabilities, let me know. I'm very happy to accommodate them. This happens. Don't be ashamed of it. It's better to talk to me now than towards the end of the class when you wish you had talked to me earlier. Please trust me about that. So anything, please let me know. And I'm happy to do it in private, over email, come office, whatever. And it's for the homework assignments. I definitely recommend doing them in LaTeX. It makes writing up the math a lot more readable for the TAs. You can turn them in any way you want, but it needs to be a PDF through Canvas. Okay, so if you want to do it in a text file, you save as a PDF. You want to write it out very clearly by hand and take a picture and save as a PDF, that's fine. But it should be very clear. Okay, if it's not clear because you used some Word or text file and you weren't able to write the math out in a way that was understandable, you might lose points. Okay, LaTeX has a great way of doing that. I've linked to some example files on here. So, you know, it takes a bit to install LaTeX if you haven't used it before, but then it's much better for writing up technical things in math. And, you know, if you're doing any writing up technical things with equations or math in it, this is the way to do it. If you submit a research paper, you collaborate with people on this using Word or something else, you'll probably get laughed at. But it happens. So if you're great at doing this in Word, that's fine. I'm not going to stop you, but I recommend doing it in LaTeX. Okay, the final thing to talk about today is we have some great TAs for this class. So that there are 3 TAs. So there are 2 of them here today. So the first one is Ankit, sitting here in front. Raise your hand or wave. Yay. So the other one is Tony. I saw him before. Okay, Tony is in back. He's one of the other TAs. The third TA is Anusha. She's out of town right now, but she'll be back, I think, later this week, and I'll introduce you to her as well. We're still working out the office hours. So I will try and generally be available right before class. I hope that'll be a convenient time for a lot of people. I may even come to this room, so we can just do it here. And then if you have preferences in other office hours, we'll probably try and post some suggested ones by the end of the week. Anusha, I posted some suggested ones for Anusha, Monday and Wednesday from 2 to 3, which is right before the machine learning class. But we'll try and post them and then get some feedback to make sure that they're not someone that says, these are all the worst possible times. If that happens, we'll try and move some. We'll also try and be available over Canvas and so forth and in other times as well. But it's best to try and stick within the office hours, especially with this large of a class. So great. So that's pretty much it for today. On Wednesday, we'll get into the first technical part of the class. We'll go over some of these basic statistical principles of these random effects and some very simple modeling, and we'll talk about these. All right, great. Well, question. The posters for them. I'll see if I can dig some of those up. I have some in email. They're just very large, so it's hard to